You to our early morning session of the 3D-SIG. It's long overdue for 20 minutes, okay? My name is Jianling Chen. I'm the chair of the first session. And in this session, we have two wonderful talks about protein design. Our first speaker is Marcel Frenkel from Duke University. He's going to talk about OSPREY, an open source software for protein design.
Good morning, everybody, and thank you so much for giving me the opportunity to talk to you guys today. So, one of the questions that we really get when we talk about protein redesign is, what can you do with protein redesign? So this is a system that I work on. It's designing an inhibitor for KRAS. And as you may know, KRAS exists bound to two cofactors, either GDP or GTP. In the GTP state, it transmits information down the cell through its effectors, and this leads to multiple cellular functions like cell proliferation. However, a single mutation in KRAS can actually cause it to become constitutively active, at which point it is one of the strongest oncogenes for cancer and actually is the most common activating mutation in cancer, being pretty much 20% of cancers. So here we have the structure of KRAS bound to one of its effectors. And our idea was, well, let's just design an inhibitor for this effector. Now, something to keep in mind is that we've known about KRAS for about 30 years, and as of yet, it's remained undruggable. So what I've done with Anna Logard, which just got the Pharma Fellowship yesterday, so we're all very proud of her, is we have here a structure of KRAS bound to the RAS binding domain of RAF1, which is one of its effectors. And what you can do, or what we decided to do, is select all the residues that were within contact distance of KRAS and just create a peptide inhibitor from that. If you were to do something like this, you would immediately be faced with multiple design options. So the first thing that you could do is a resurface design. We just exposed a bunch of very hydrophobic amino acids that now have to be resurfaced to remain the protein, to make the peptide soluble. The other thing is that you need to stabilize this fold. So this fold only exists in context of its domain. So you need to make this fold stable. And finally, you also have to redesign the interface for increased binding. If you want an effective inhibitor, you actually have to have an interface that has improved binding, so what we call super binders. So now taking you a little bit up into a toy example, or into a more generalized example, if you imagine that this is KRAS over here, and this is our inhibitor peptide, and this is their interface, the way you would go about setting up an interface design is that you would select the residues that you want to mutate, and those are shown here by disappearing. And you would also select what energy function you want to do and what rotamer library you want to use. And this includes the rotamers and the amino acids that you want to use. And then if you were to do this with OSPREY, what you would go about doing is you would do dead end elimination, followed by our dynamic A star, followed by our epsilon approximation to the partition function, what allows you to calculate K star score. And what this K star score is that it's the partition function of the bound complex over the partition function of the unbound complex, unbound proteins, and this approximates Ka. And one of the benefits of using this method is that it's provable, which means that you're actually having a complete search over the space. And what this complete search over the space does is that it pretty much guarantees that if you don't get the result you want, you're actually having problems with your model, because these provable algorithms are provable in accuracy towards the model. So, and what our model gives, these design would give out to you is not only the conformation, the shape, but also the amino acid sequence of the best binders. And here you can see us doing a combinatorial design over multiple rotamers and residues. So if you are provable towards your model, So you know that if you have any error, the error is in your model. What we decided to do is always work on improving the model. So the OSPREY model, as you call it, contains two quite important and what we think pioneering attributes, which is our continuous flexibility and our entropy aware. So if we were to talk about continuous flexibility, what you can see here is the rotamer map for isoleucine. And what you see distributed here are the best structures from the library selected by the Richardson's group at Duke. And this is the son of penultimate rotamer library. And what you see is that there's a distribution at different positions. And these distributions exist even at the very best crystal structure, suggesting that this is a real distribution. However, most design softwares will actually deal with rigid rotamers, which are these tiny red dots over here. And as you see, these dots don't really represent the actual sampled space. So what we decided to do is we work in a continuous framework by actually treating each rotamer as a voxel. So in work done by Pablo Gonza and Kyle Roberts, what we can see is that even for the same rotamers, if you just allow for local minimization within those voxels, you can go from clashes to actually what is the best structure. And a more visual representation of that can be seen here. So all these residues are within their rotamers. And you see that very small oscillations within the voxels due to clashes, shown here in red and purple dots, to really good van der Waals overlaps, shown in green and blue. So if you want a more systematic analysis of this, what you can actually see is that over here we have the energy in kcal per mole of the GMEC, or the global minimal energy conformations, for different PDBs. And if you're in a rigid framework and you're trying to find for a given backbone what's the best sequence that would fit that backbone, you're actually seeing these energies over here. Whereas if you allow for continuous rotamers, you actually find energies that are much lower. Maybe more important for biochemists like myself is that the sequence, and here we see the fraction of amino acids that differ for the GMEC, or the global minimum energy conformation, between the rigid and the continuous, actually changes quite significantly when you allow for continuous rotamers, meaning that you're actually getting different answers, which experimentally means you're actually going to be testing different things. Finally, OSPREY is entropy aware. So the way our K-star algorithm approximates the Ka of binding through an approximation of the partition function of the bound and unbound proteins. And what this allows us to do is actually to calculate an ensemble. And this ensemble takes into account some of the entropy. So because from Ka we can approximate delta G, and we know that delta G has an entropic component, we know that we actually are taking into account this conformational entropy, which if you do not, you simply can't see with your designs. Moreover, when we calculate delta G, which is the improvement versus your wild type, you actually get quite a few entropy options, being conformational entropy, translational entropy, and rotational entropy. So if you were thinking about how this looks from a designer point of view, here you have a single conformation model where you have the complex on top and the individual proteins in the bottom. It's pretty much like that. And this is what you have with the entropy-aware OSPREY models. So here you can see that you're actually looking at a thermodynamic ensemble. This is a real thermodynamic ensemble. And what you can see here is you have both rotamer flexibility and backbone flexibility. So sidechain and backbone flexibility in these designs. So this model has actually allowed us to have some experimental successes. So it's been validated in experiments. And what we see here is that it's been validated in multiple classes of experiments. So here we have an enzyme redesign. Here we actually have the design of a peptide inhibitor. We have a design of an allosteric small molecule, of antigens. Very exciting, recently we started work on predicting resistance mutations to novel drugs before they've been observed in the clinic, which is very exciting work. And also what we've been able to do is redesign antibodies. And this over here is a C4 binding site antibody that binds to the to HIV, to the GP120C4 binding site. And it's actually currently ongoing into 3 clinical trials. So it's very exciting to see some of our work making it into the clinic. So although we've had a lot of successes, there were obstacles for using the previous version of OSPREY. And these obstacles, I'll go through them one by one. So what we've actually done and what we're presenting here is that we've taken OSPREY from pretty much this in version 2 to this in version 3. And what that means for the user is that if you're talking about size of designs, which were limited, and they were limited because our search speeds were actually not fast enough, and because our memory demands were way too high. So in work done by Dr. Jeff Martin, which is here today, we've been able to do significant improvements to this, and these improvements have been mostly engineering, or that's what I'm going to show you now. So for single thread optimization, what we see here is that OSPREY has actually become 400 times faster than OSPREY 2.2. This is running on exactly the same hardware with exactly the same software, so this is purely engineering improvements. And what you can see here is that this is the OSPREY time for running a design. This is the OSPREY 2.2 time for running a design. Each one of these dots represents a design. And you can see there's a whole new class of designs that were not possible to be done with OSPREY 2.2 that are possible with OSPREY 3. The other thing that we're very excited is that beyond this 400 times speed up, we've also made it about another 10-fold faster, especially for large designs, by adding GPU acceleration for our minimizations. And finally, we've done a lot of work to drastically reduce the amount of memory that OSPREY does, and this has allowed us also to do much, much larger designs. So the other problem that we had is that that K-star algorithm that I showed you before was linear in the number of sequences, which meant that if you had 10 million, 100 million sequences, you would have to look at them one by one. So we're very excited that we've actually been able to overcome that. And now we have a BBK star algorithm that's sublinear in the number of sequences. And what you can see in this graph over here is that if n is the number of sequences that you have to look at, and on the x-axis you have the total number of sequences, this green line represents the exhaustive search, which was our previous best approach. And currently, we actually only have to look at much fewer sequences to get you the best answer. And if you want a number on it, it's actually 1 in 100,000 sequences. So you have to look at much fewer sequences to actually get your best answer. And if you're looking at how fast this is, so this is time of runs, and BBK star is up to 1,982-fold faster than the previous algorithm. And this is in addition to the about 4,000-fold speed up that we just showed you. So we're a lot faster. So finally, this is actually very exciting. We were previously limited to pairwise energy functions. So by using LOOT, which is a technique that transforms a continuous space into a discrete one, and I'll be happy to tell you guys more about this later. Right now, it'd be too long. What we've been able to do is actually double the amount of flexible residues that we can design with. And if you imagine that we are exponential in the number of residues, this actually means that we've been able to exponentially increase our space, our flexible space. But maybe more exciting is that this is a design done with the Amber force field. Now we can actually use n-body energies, functions like the Boltzmann, which represent a better representation of physics, and therefore probably more accurate scores. So finally, OSPREY had limited backbone flexibility. So what we've been doing and doing is doing continuous larger motions to our backbone flexibility while keeping experimentally motivated backbone movements. And what this means is that we've developed this larger search space using the algorithm called CATS. And this work is done by Dr. Marcel. And what CATS does is it keeps all the angles as well as the bond lengths the same while allowing you to move the dihedral angles. And what this guarantees is that you're actually doing movements that are things that you would expect the protein to do. You're not introducing non-realistic movements. Finally, the OSPREY UI was difficult and disorganized, and only users with advanced programming skills could use OSPREY. So what we've done is that we've moved to a Python interface. So what you see here, it might be a little bit hard to see on the screen, but this is actually all you would need to do to run a design. This is a simple design, but it's a full design. And the user, if you wanted to make alterations between designs, would probably only need to alter this small section over here. So in about 10 lines of codes, you can actually be doing a design in OSPREY. And maybe even more exciting is that we have a really nice documented API, which allows you to look up new functions as well. So for users, we hope this makes it a lot easier to use. So I've just showed you that OSPREY 3.0 is faster, it has some nice new features, and one of the questions that we get is how accurate is it? So what we did is we looked at a preliminary benchmark here where we had 58 mutations over 4 systems, and on the y-axis you have the K-star rankings, which are our calculated rankings, and on the bottom you have the experimental rankings. And the way these rankings are done is that the top mutation is the #1 ranked, and the bottom mutation is the last ranked. And if you actually get a Spearman value between these rankings, you actually get 0.762, which we think is very good. And if you want to look at examples, so this is interferon binding to its receptor, and we correctly predict this mutation from arginine to glutamate that would reduce binding. So this decreases binding, and that's kind of clear to see. However, OSPREY is always also picking up into things that are harder to understand, as this mutation over here, where we actually see that the mutation to an alanine actually increases binding. Sorry, that's a typo over there. It actually is increasing binding. So for people that don't want to use OSPREY, OSPREY 3.0 is open source, so you can take it and do it what you want, or you can use it as is. The release is available from GitHub, as is the source code. And we actually have a paper that just got accepted to JCC, which highlights these results as well. I would like to acknowledge my fantastic group. Here's a picture of us outside of Duke. And I'd also like to thank ISMB for the travel fellowship, which allowed me to come here and talk to you guys today. Thank you.
What about negative design incorporation?
Yeah, so for instance, that example that I gave you where we predicted mutations, the way we do that is that we can do multi-state design, which has pretty much as many multi-states as you want. And the way we did that is that we had a negative design set up for the new drug and a positive design set up for the actual substrate. And by comparing what mutations actually allowed for the substrate to bind and didn't allow for the drug to bind, that's how we were able to predict resistance. So it's something that we're very invested in, and we believe that our software could do extremely well. So yeah, it's a very important part.
Yes, at the very beginning, so you talked about ROS binding, and
Yeah.
the GDP and GTP, they are all small molecules, and in the experimental setting, you have to compare the delta G between small molecule and the protein, but OSPREY, it doesn't seem like it calculates small molecules.
So so as I was saying about this resistance prediction, it was actually work done in small molecules. So OSPREY can deal with small molecules, and we actually understand that's an area that out of the box, it's kind of hard to use. So there's efforts towards involving in that, towards that direction. For that particular design, the GDP and GTP have picomolar affinity. So, and they exist in micromolar concentrations in the cell. So it's almost impossible to outcompete. So that's why we chose to actually do a peptide inhibitor on the interface rather than try to outcompeting the small molecule drugs there. Outcompeting GDP with small molecule drugs.
So you're not competing the small molecule?
No, we're not. That would be, people have tried in the industry for about 15 years when they first discovered the molecule, and it was absolutely infeasible. So.
Okay. Unfortunately, we don't have more time for more questions. You can talk to the speaker.
Okay.
All right.
Thank you very much.
Let's thank the